Okay, so this is the optional part in which I discuss Galilean invariance of Newton's laws. Now, Newton's first law is, will deserve trivial discussion here because we are restricting ourselves to inertial frames, and inertial frames, by definition, are frames in which Newton's first law works. Okay, so in all the frames, in all the reference frames in question, Newton's first law works. In other words, objects in motion stay in motion, and objects at rest stay at rest. So this is already assumed, this is already a priori true in the frames that we're discussing. The big one, though, is Newton's second law. So we want to discuss invariance of F equals ma, right? Newton's second law, you know it as F equals ma. And if you really want, you can put arrows because it's a vectorial law. It's a vector equation. Now, written in this form, this is certainly true. This is Newton's second law, but it's not really how it's used. In mechanics, you probably used it like that, right? So you solved silly problems like blocks sliding down inclined planes, and you decomposed the forces. You applied the forces along the direction of the block's motion, and so on and so on. That's not really mechanics. That's not really using Newton's second law. The reason you spend so much time doing that in introductory physics is so that you're able to understand that forces are vectors. But how does Newton's second law actually work? Like, what does this mean? How do we use it? What's it good for? So consider the following mechanical system. You have two masses on a spring, right? So this is object one, this is object two. It has mass one and this has mass two. And there is a spring with spring constant K. And these are also, the spring is described by L equal rest length of the spring. So if the spring, if the separation between the two masses equals the rest length of the spring does not exert force on each mass. Or equivalently, you could say mass one does not exert force on mass two by means of a spring. Spring is a mediator of the force of object one and object two, and vice versa. So force of 2 on 1 is given by minus k, I'm going to do this in one dimension, x1 minus x2 plus L. Okay, notice that, so let's say that this is the x coordinate, right? So if x2 minus x1 equals L, right? X2 is L further along the x-axis than x1, then x1 minus x2 will be minus L, and this whole expression is 0, as advertised. If x2 minus x1 is bigger than L, and x1 minus x2 is negative, I'm sorry, it's more negative. It's more negative than minus L. Then you get a negative quantity in the parentheses times negative. You get a positive, right? And 2 tries to pull 1 to the right. So it works correctly. And so the way you would apply Newton's second law is you would say mass times the second derivative of position of object 1, this is force on 1, equals minus k x1 minus x2 plus L. And equivalently, so this is mass 1, and equivalently, so this is the acceleration of object 1, and this is the force on 1. So this is F equals ma. So this is the force on 1 equals mass 1 times acceleration of object 1. And mass 2 times the acceleration of object 2 equals, by Newton's third law, it's same magnitude, opposite direction, right? Action equals reaction. So it will be given like this. So if force applied by 2 on object 1 is positive, then force applied by object 1 on object 2 will be automatically negative. So Newton's third law is sort of built into this force law. This is Hooke's law. Now you probably know a simpler situation where you have a mass attached to a wall on a spring of rest length L, and you measure the displacement away from that equilibrium position, right? So if you have that situation, right? So for what I just drew right here, then these general expressions will specialize to minus kx, which you're more familiar with, where x here, it's really this whole glob of stuff right here, that's x. Now, this probably already looks pretty darn scary to you because you probably have not seen anything like this. This is what Newton's second law really is. It's a differential equation where the forces are expressed as functions of coordinates, could also be velocities, and the accelerations are expressed as derivatives of coordinates. Okay, so let's say there is an experiment. Let's say we put this mass, two masses on a spring on a frictionless table. And what would it do? Well, it would just sort of oscillate like that, back and forth. Let's say that this is in frame S. And let's say now we are observing this whole thing from a moving car, train, bus, whatever. So this is our frame S prime that's moving with velocity v, the usual scenario, right? As seen from that bus, what we will see is we will see this oscillating system just moving back. We'll just say bye-bye, right? So this pairs of masses, as they're oscillating, they're moving back from us. So in the lab, I see this. From the bus, I see this, right? So as this thing is oscillating, it's also moving back. So let's say, so if in frame S, this applies, right? So if in frame S, we have m1 second time derivative, x1 equals minus k x1 minus x2 plus L. So this is the equation that describes the motion of object 1, and there's a similar equation for object 2 in frame S. Now let's try to see what kind of a law of motion, what kind of an equation object 1 and object 2, what kind of equation these two objects are described by as seen from frame S prime. Well, let's see. So we have x equals x prime plus vt, right? So x prime equals x minus vt. You take one derivative, you get that's the velocity addition, right? So this is the position Galilean transformation. This is the velocity Galilean transformation. And what about acceleration? Hit it with one more derivative, right? So second derivative with respect to time equals second derivative with respect to time. What happens to this? Well, 0. So as if frame S is an inertial frame, then if frame S prime is moving relative to S uniformly, it's also an inertial frame. And if the second frame is moving uniformly relative to the first frame, then while the velocities would be different, the accelerations would not be. So in other words, imagine you have two co-moving cars and you're watching something accelerate. You would disagree about the velocity of that object. Let's say it's a bird that's slowing down. You would disagree about the velocity of that object, but you would agree about the value of the acceleration of that object. What if the second frame is accelerating relative to the first frame? In other words, v, the relative velocity between the two frames, is not a constant. Well, then you would not get a zero, and then the accelerations would be different. Then you would not agree on the accelerations. And so if something, let's say frame one is inertial and frame two is accelerating relative to it, so generally it means that it's not inertial, then if you observe some object, you would not agree on the acceleration of that object. And that extra term that would come with dv dt, it's zero if it's constant, but if it's not constant, it's not zero. That extra term gives rise to something called fictitious forces, or sometimes it's called pseudo forces or effective forces. And in homework one, I give you a link to a video called Frames of Reference, where they describe these kinds of effective forces that arise when you observe something from a non-inertial frame. In their case, they give an example of observing something from a carousel. Carousel is an accelerating frame, generally not inertial. And you would think that this object experiences some kind of a force. It's not a real force in the sense that it doesn't correspond to any kind of a physical interaction. Remember, when you have a force, you have to ask, what's the nature of the force? Is it a frictional force? Is it a gravitational force? And so on. Does it correspond to any kind of a physical push or pull? Those effective forces, they don't correspond to any kind of a physical agent or physical push or pull. But you would say, well, but there's got to be a force because that's the only way in which I can explain the motion. We will not deal with this situation. We restrict ourselves strictly to inertial frames. So if frame one is inertial, frame two is inertial, frame two is moving uniformly relative to frame one, so frame two is inertial. Okay, so the accelerations are the same. So you would say, sorry, I forgot to put a prime. So you would say that A prime equals A, right? So that's the left-hand side, right? So the left-hand side would say m1 times the second derivative of x1 prime. What about the right-hand side? Well, note that if the transformation between two coordinates is given by that, that x1, then x1 minus x2 equals x1 prime plus vt minus x2 prime plus vt. And you can see that vt's cancel and x1 prime, x1 minus x2 equals x1 prime minus x2 prime. So now we're ready to substitute. Okay, so x1 minus x2 is x1 prime minus x2 prime. And the second derivative of x1 equals the second derivative of x1 prime. And what we get is, we get m1, the second derivative of x1 prime with respect to time squared equals minus k. Let's see, so this is going to be x1 prime minus x2 prime plus L. And you can conclude that the equation has the same form. Same form. So again, this idea of form being preserved as you go from one frame to another, that's the idea. The only thing that changed is instead of the position coordinates x in frame S, you use the position coordinates x prime from frame S prime. You can call position coordinates x sub s and then x sub s prime, x subframe A and x subframe B, or position of frame A and position of frame B. The point is, the physical content of this law of motion is the same. It says that, well, mass times the acceleration of object 1 in this second frame is given by minus the spring constant times the difference between positions plus L, times the quantity difference between positions plus L. That's the physical meaning of this. And the physical meaning of this is the same. Both equations tell the same story in their respective coordinate systems. That's what it means to say that the form is preserved. So the upshot is that the upshot of this is that you would say that laws of motion, you see, this is an example of a law of motion. This is an example of a law of motion. This is these are examples of laws of motion. So when you express Newton's second law as a differential equation, it becomes a self-consistent expression that describes the motion of objects in the system. And so you would say that laws of motion are the same. In the two co-moving frames. And again, we have in mind inertial frames. Both frames are inertial, right? Or if frame 1 is inertial, we imagine that frame 2 is moving uniformly relative to frame 1, that it's also inertial. So remember, I discussed that laws are really a relationship between quantities. And the fact that they have the same form, that means the relationship between accelerations and positions is of the same form. So what is it about Newton's second law, and what is it about properties of forces that led us to this idea that they take on the same form in two frames? And the key here is that the forces, being functions of coordinates, are functions of the differences of coordinates, right? So you see, forces are interactions. You have object 1 interacting with object 2 by means of a spring. What's another example of a force? Well, force on a pendulum. Force on a pendulum is a force of interaction between the Earth and the pendulum. What's another example? Force of Earth on the moon. That force quantifies the strength of interaction between the Earth and the moon. So as long as forces between objects, which generally depend on coordinate objects, depend specifically only on the difference of coordinates, this magic will happen. Because notice, it's because the force is a function of the difference of coordinates that VT's cancel. So as long as forces, being functions of coordinates of objects, are more restricted to being functions of differences of coordinates, this will apply, right? So this happened or another way of saying that is it's a function of relative coordinates. Coordinate of object 2 relative to object 1. I can give you another example. So this is example 2. This is example 2. This is going to be, let's say you have sun and the earth, right? So this is sun and this is earth. I'm thinking if I should do this in full vectorial form, but yeah, let's do that. So force of, so this is object 2 and this is object 1, for example, of 2 on 1. What's the force of sun on the earth? Well, it's G times M divided by what? Divided by the distance. And the proper way of writing that is position vector of object 1 minus position vector of object 2 squared, divided by distance squared. Now, you're probably used to seeing just D in the bottom. And that's okay. So if we place an origin of coordinate system at the center of the sun, or at the center of mass of Earth-Sun system, you can do that. But let's say you're an alien, you're observing this whole thing from some distant planet, and you could say that this is a position vector to object 2, and this is a position vector to object 1, right? Then, right, so this is your some origin from far away. Then you would write something like what I wrote. If you want a fully vector form, right, so this is just the magnitude, and this is force of 2 on 1, and here's how the vector form would look like. Let me write it like this: 2 minus 1 cubed times R2 minus R1. Let's see if this makes sense. So if this is, let's say I have a coordinate system, I have R2 and I have R1. You know that object 1 is going to be attracted to object 2 because it's gravitation. This vector right here is R2 minus R1. So R1 plus R2 minus R1 gives R2, right? So the force on R1 is in the direction of the vector R2 minus R1. That's why I wrote it like that. Okay, so what would Newton's second law look like? Well, it would be mass 1 times the second derivative of the vector position of object 1. Now, you might be scared of this, like what's the derivative of the vector? But, well, if you really wanted to take the derivative of the vector, what you do is you take the derivative, the time derivative of each component, and just include I, J, and K hat, I hat, J hat. So this looks like this. It's kind of in a wrapped notation, right? In a compactified form. By the way, R1, this is the same as this. I can write it like that. R1. Long story short is that R2 minus R1, when you switch to a moving reference frame, this will turn out to be R2 prime minus R1 prime. So for example, if R2 minus R1 is 10 meters in the southeast direction, then R2 prime minus R1 prime would also be 10 meters in the southeast direction, okay? That's the beauty of, you see the difference, the difference of coordinates. You see the Newton's law of gravitation, this is Newton's law of gravitation, the inverse square law. It's not just some ad hoc formula. It's a Galilean invariant formula. Why? Because the coordinates appear as differences of coordinates, okay? So it's not just any odd formula. The difference, all the coordinates in expressions for forces are differences of coordinates. It could also be differences of velocities, right? So for example, drag force between a parachute and the air depends on the velocity of the parachute minus the velocity of the medium in which the parachute is moving. So same idea could apply to velocity-dependent forces. There are also differences of velocities. Then they would be Galilean invariant. So if you apply the same reasoning, you would find that in frame S prime, let's say you're observing the Earth-Sun system from a moving spaceship. I know this is going to be a mouthful with all these primes. And again, that's why I say this is an optional video. So if you're too stressed out about what I'm saying, or if it's beyond your head, well, then don't feel too bad about it. It's an optional video. Because the forces are functions of differences of coordinates, the VT cancels, and we obtain an equation describing the Earth-Sun system that has the same form. The form is preserved. The physical content of this equation of motion is the same. The law of motion is the same. Okay, so I gave you two examples. I gave you two specific examples, and then this can generalize. As long as a force between two objects depends on the difference of coordinates of those objects or differences of velocities. Sometimes you have velocity-dependent forces like drag. Then the form of F equals ma, when you write it in terms of derivatives and coordinates, the form would be preserved. And the only thing that's different from one coordinate system S to another coordinate system S prime is that in one coordinate system, you express forces in terms of coordinates of that coordinate system, and another, you express it in terms of coordinates of the second coordinate system. But the form is the same, the physical content is the same, and the law of motion is the same, okay? This was pretty mature. Oftentimes, you know, this discussion is often skipped. And when it's not skipped, it's done incorrectly. But I wanted to present, to give you an honest presentation of how you take a law of motion encoded by Newton's second law, and how that law of motion is, how that resulting law of motion is Galilean invariant with respect to reference frame change. And along it, you saw how we actually use Newton's second law, right? We express forces as functions of coordinates, and we express accelerations as derivatives of coordinates. So perhaps you already took dynamics and maybe you've seen this already, then it's not that much of a shock. If you have not taken dynamics, this might be a little bit uncomfortable. That's okay, okay? The point is, Newton's second law is Galilean invariant, okay? So now you can sleep peacefully. All right, well, I hope this was entertaining, and I will see you in the main section, okay? See you, bye.